Hello and welcome to the RC Circuit Lab. In this lab, we're going to be looking at the charging time for a capacitor. What we have here is a voltage supply that's going to give us what's called a square wave, which is just a source of positive voltage. It ends up being about 4 volts, charging the capacitor in pulses that occur about once every 0.1 seconds approximately. So here's our circuit board right here, our lab. We have some wire to hook things up right here. You'll notice this right here. This right here is a 1000 ohm resistor. If you were to look at the bands on it, you'll see brown, black, and red. Brown is 1, black is 0, and red is 2. You also see a gold band there at the end saying that this is, to good tolerance. So that would be 1, 0 times 10 to the 2. Or 1000 ohms. So there's your 1000 ohm resistor. This right here is your capacitor. As you can see right there, it's 330 microfarads. Just to let you know, tolerances on capacitors aren't very good. It could be anywhere, plus or minus 20%. We also have our voltage sensor right here, or our voltmeter, and we have some leads to hook everything up. In the next video, I'm going to show you how everything's hooked up, including the voltmeter, and we'll talk about how the experiment works. So this is the experiment as set up. As you can see over there, it's hooked up to our data acquisition unit, which also in turn controls the voltage here. This applies our voltage positive side here, going through a resistor, then going through our capacitor, and then back in, like that. So the idea here is that we start with a discharged capacitor. We start our experiment, and as the capacitor charges, we measure the voltage and look at the relationship between the resistance, the capacitance, the charging time, based off of the data that we get, to see if the theoretical capacitance that you see as per the experiment and from the data is the same as what you see on the capacitor itself right here. All right, we'll talk more about this in the theory section, and I'll see you then.
Hi, and welcome to the theory section for the lab on RC circuits. Now in this lab, we have a circuit that has a power source that's connected to a resistor and is also connected to a capacitor. Now what's relevant in this lab is the type of voltage that we are sending to our circuit. If you've read the description to it, you know that we have a square wave with a period of about 10 seconds. The frequency is 0.1 seconds, or 0.1 hertz rather. So it's a period of 10 seconds. And so what square waves look like is like this. According to the lab instructions, you want your square wave to always send positive voltage. So you turn your circuit on, and then according to the lab, it starts at 4 volts. It stays at 4 volts, stays at 4 volts, stays at 4 volts, stays at 4 volts, and then what it does is it drops off to 0. And then it's 0, 0, 0, 0, 0, and then it goes back up to 4 volts, stays at 4 volts, drops off to 0, and so on. The shape of which, were you to plot the voltage as a function of time here, would give you this square look to it. It's a square wave. So one way you can visualize this is that you have a RC circuit that has a constant voltage, and then suddenly the voltage stops. So this would be analogous to you opening up the switch and letting the battery be diverted and the capacitor discharged to the resistor. From charging standpoint, you can think of the charging of this capacitor as being a consequence of the potential that's sitting here in this voltage driving current through the resistor, so it can deposit charge onto C. But when the square wave drops off to 0, that voltage is no longer present. And so what happens is the capacitor sort of rises to take take over, and then charge flows from, in this case, this would be positively charged and this would be negatively charged. So you would have current run this way basically through. Current here is running this way for the charging. So what you have really are sort of two problems when it comes to solving what's going on. If you were to use sort of your ubiquitous Kirchhoff loop rule to sort of figure things out, in what I'm going to call circuit 1 over here, you have your voltage source, and then you have the voltage across the resistor, and then you have the voltage across the capacitor, and those add out to 0. Now with the discharging situation, you have no voltage source, because what's happened is the square wave has dropped down to 0. And here really it's just VR plus VC is equal to 0. So for this one right here, if you look at the way the voltage across your capacitor behaves, what you need to do is you need to solve this differential equation. V being the voltage source, VR being given to us by Ohm's law, and the voltage across the capacitor given to us by the relationship between charge, capacitance, and voltage, which would be Q over C. For the discharging situation, really it's just IR, which is the voltage across the capacitor, plus Q over C is equal to 0. So let's look at part 1 to begin with, and then we'll talk about part 2 here. So for part 1, if you note the fact that your current here really is just how the charge changes with respect to time. That is the definition of current. Then what you have here is a differential equation that looks like this. Now it's called a differential equation because it has derivatives in it. And really what we're looking for here would be the voltage across the capacitor as a function of time. So if you sort of rearrange this, if you put this, we'll say, onto the right hand side, and then you switch sides, what you have is dq over dt times r is equal to is equal to v minus q over c. Now what we're going to do is we're going to move this to the left hand side, move this to the right hand side, and then divide both sides by r. When you do that, that's dq over v minus q over c. And on the right hand side you would have a dt over r. Now just to make a little bit of space here, let me move what I was talking about here. We'll see over here. I'll do my work on this one over here. So that said, when your circuit starts off, when you flip the switch and you start your voltage going, what happens is your capacitor starts off with a charge of 0 and builds up to a charge of, we'll call it Q. Those would be the limits that you would integrate over here. Your time starts off at 0. You notice the fact that the resistance is constant in this case. And that's what you're stuck right there dealing with. Now, the right-hand side of this equation is pretty easy to integrate. This is just dt, integrated from 0 to t, which is going to give us t. This one right here is a little more complicated, but not so much more. We'll use a substitution there. U is equal to v minus q over c du. Therefore, it's going to equal to minus 1 over c, dq. So every time I see a dq, I need to put a minus c times du there. And so on the left-hand side, if I plug in the limits here, I have a v on the bottom. On the top, I have a v minus q over c. And then I have a minus c sitting out in front because of this, and c is constant. And really what I'm integrating is du over u. So we know this is going to give us a natural log. On the right hand side, if you just go ahead and perform the integration, you have t over r. So what I'm going to do is to go ahead and integrate the left-hand side. I'm going to move this minus c over here to the right-hand side. And when I do that, on the left-hand side, I end up with a natural log of u evaluated from v to v minus q over c. And on the right-hand side, I end up with a minus t over rc. Now here's our time constant right here, tau, which is equal to r times c. Not r times r. There we go. So let me box that, just like that. And now, if I go ahead and plug in my limits of integration and do my logarithm substitution rule, I end up with a v minus q over c on the top, and then a v on the bottom. And on the right-hand side, it's still a minus t over tau. I'm just going to go ahead and plug that tau in. And now we're going to take and raise e to the power of both sides. And we do that. When we do that, we end up with a v minus q over c on the left-hand side. And on the right-hand side, if I just go ahead and move that v over here, with a v times e to the minus t over tau. And then move this to the right-hand side, move this to the left-hand side, switch places. And then what you have is the following: q over c is equal to v times 1 minus e to the minus t over tau. Now what's q over c? Well, if you remember the relationship between q, v, and c, what this is the voltage across the capacitor. So we'll call that v sub c. So for charging here, v sub c is going to equal to whatever the voltage of our power source is times e, times 1 minus e to the minus t over tau. So this right here is going to be the relationship that's going to describe the voltage of our capacitor as a function of time and as a function of our initial voltage, and obviously as resistance capacitance as well. Now with this charging, if I sort of do the same procedure here, the current is dq dt. You have your R right there. You have your plus q over c is equal to 0. I'm just going to go ahead and divide both sides by r and move this over here to the right hand side. So when I do that, I get a dq over dt on the left hand side. On the right hand side, I get a minus q over rc. And once again, we see our time constant here. That is a minus q over tau. And now it's just an issue of moving q over here to the left-hand side so we can integrate it, and then moving t over here to the right-hand side. So we'll start with dq over q on the left-hand side. On the right-hand side, I have a minus dt over tau. And now we're going to integrate. Now here, when you discharge, you start off with a full charge, which I'll call q naught. You end up at 0 or some q at some point in the future. So we have a dq over q there, and on the right hand side, we have our integral of from 0 to t of dt. Starting our discharge time at t is equal to 0 in this case. So this is pretty easy. You have a natural log of q over q naught on the left hand side. On the right hand side, you have a minus t over tau. And then you just, raise e to the power of both sides. And when you do that, you end up with a q is equal to q naught times e to the minus t over tau. Now, if I were to divide both sides by c, kind of like if you look over here, q over c is equal to v sub c. So if I divide both sides by c like this, what we have here is the source voltage, which I'll call v naught. And right here, this right here would be the voltage across the capacitor. So the voltage across the capacitor in this case would just be equal to v naught times e to the minus t over tau. So here, v sub c is equal to v naught. I'll go ahead and call this v naught just to be consistent with what I did below. Kind of like that, our initial voltage. And that's e to the minus t over tau. So now if you look at these things, here's what we expect. So you start your thing off, like this. We'll say that this is time, and this is voltage. So what happens is if you look here, when T is equal to 0, your voltage across your capacitor is 0. Okay. And it's going to build to whenever it hits its peak charge, it's going to build to V naught. As T goes to infinity, this goes to 0, which means that your voltage across your capacitor ends up being the same as the voltage across the battery. So what you would expect to happen here would be you turn this thing on, and what happens is the voltage builds and it builds and it builds, and it's going to look like this sort of plateauing exponential, and then it's going to get to like this. And at this point right here, we're at whatever our source voltage is. Then what happens is our source, since it's a square wave again, shuts off, and at that point now you're in the discharging situation. You start off with T is equal to 0 at that point, which means you're at your maximum voltage, and then it decays exponentially. So what's going to happen is it's going to go like this. Okay. So we should see something like this whenever you plot your data, and that's the reason why. Okay, so that's it for the theory section, and I'll see you in the next lab.